Hello students and welcome to the 16th lecture in the lecture series for the course of Artificial Neural Networks for Electronics and Telecommunication Engineering students of the 7th semester Goa College of Engineering. I am Ms. Purti Savardekar, the faculty in charge for this course. In the last class, we studied that in a pattern recognition system, the classifier identifies the pattern space as a space with decision regions which are separated by decision surfaces. We learned that each decision region is represented by its discriminant function gi of x. If the pattern belongs to the ith class, the discriminant function for that class will return the highest value. That is how a maximum selector can generate the class of an input pattern. We also learned that the equation of the decision surface separating the two classes represented by gi of x and gj of x is g of x, which is equal to gi of x minus gj of x equal to 0. G of x equal to 0. Let us discuss this further today. A dichotomizer is a special case of such a classifier where the number of decision regions R is equal to 2. Therefore, class 1 is represented by the discriminant function g1 of x and class 2 is represented by the discriminant function g2 of x. The decision surface between these two regions is where g1 of x is equal to g2 of x, which gives the equation of the decision surface as g1 of x minus g2 of x equals 0. This can be written as g of x equals g1 of x minus g2 of x equals 0. That means for all the patterns lying on class 1 side of the decision surface, g1 of x will be greater than g2 of x, which means according to this equation, g of x will be a positive value. G of x will be greater than 0. On the other hand, for all the patterns lying on class 2 side of the decision surface, g2 of x will be greater than g1 of x, which means according to this equation, g of x will be a negative value. G of x will be less than 0. This is what we've been doing all of this while obtaining the equation for the line to design neural networks. Therefore, the general classification rule for a dichotomizer can be given as g of x greater than 0 is for class 1 and g of x less than 0 is for patterns belonging to class 2. Because of this, for a dichotomizer, you don't need a maximum selector. You only need to check for the value returned by g of x. If it is positive, the pattern belongs to class 1, and if it is negative, the pattern belongs to class 2. This job can easily be done with the help of a TLU. This is exactly what we've been doing. We have been training using learning rules to obtain the coefficients of the discriminant function of g of x. The coefficients of the discriminant function g of x. The aim for today's lecture is to derive a formula to obtain the equation of the decision surface when prototype points for each class have been given. That is, given a pattern representing each class, we could obtain the equation for decision surfaces between the classes in the pattern space. We first start with the concept of Euclidean norm. The Euclidean norm or length of an n row vector x is denoted as norm of x and defined as the norm of x equals x transpose x, the whole root. If x is a metric column vector given as x transpose equals x1, x2 and so on up till xn transpose, then the norm of x is the product of the horizontal vector x1, x2, xn and the column vector x1, x2 up till xn. The product of these two, the whole root. So, the norm of x is given as, if you multiply the two matrices, you will get the whole under root x1 square plus x2 square plus up till xn square, which is the norm of x equals the whole root of xi square, where I goes from 1 to n, summation of all of that. So this is what the norm of x is. Let us now try to understand the concept of Euclidean distance. Euclidean distance is defined as the minimum distance between any 2 points in the Euclidean space. For example, if x1 is equal to x11, x12 and x2 is equal to x21, x22, then the Euclidean distance d between them is given as, you know this, d12 is equal to under root x11 minus x21 the whole square plus x12 minus x22 the whole square. If you observe this carefully, you will obtain this expression if this is the product of the two matrices, right? Like this, x11 minus x21 as the first element of the horizontal matrix and x12 minus x22 as the second element of the horizontal matrix, and these two written as a column vector. If you find out the product of these two, you will get exactly what you have here, x11 minus x21 the whole square plus x12 minus x22 the whole square under root. Yeah, so we can write it this way, just confirm. But what is this term inside the matrix? x11 minus x21, x12 minus x22. This can actually be written as x11, x12 as one matrix minus x21, x22 as the second matrix, which is actually equal to x1, capital X1 minus capital X2, the 2 points. That's why we can write d, the distance between 2 points, as under root d12 equals under root x1 minus x2 transpose x1 minus x2. Verify. Please verify. So, d12 equals x1 minus x2 transpose into x1 minus x2 the whole root. Does this look familiar? Yes, we've just learnt it. It is the formula for norm. The Euclidean distance d can be given as the norm of x1 minus x2. d12 equals norm of x1 minus x2. In general, dij is equal to the norm of xi minus xj. I request you to pause this video here for a minute or two and go through the two definitions and understand the concepts. Now, to find the class or region to which a pattern belongs, we need to find its Euclidean distance from each of the region. The Euclidean distance from each of the region. Consider this pattern space with n number of clusters belonging to n different classes. Let x1 be the cluster centroid point or the prototype point for class 1 pattern. Let x2 be the cluster centroid or the prototype point for class 2 pattern, and so on up till n classes. Now consider pattern x whose class membership we want to find. For this, we need to find the Euclidean distance between the pattern and each cluster centroid. This distance, we will say the distance is dx x1, dx x2 and so on up till dx xn. The pattern x will belong to the ith class if dx xi is minimum. Dx xi is given by dx xi minimum is given as norm of x minus xi minimum. We've seen this. Norm of x minus xi minimum, because we want to find out the minimum distance, which can be written as x minus xi transpose into x minus xi under root. Now, if the root is minimum, its square also is going to be minimum. So we get rid of the root sign and we square the distance. Distance xxi dxxi the whole square minimum is equal to x minus xi transpose into x minus xi minimum, which is expanded now further as x transpose x minus x transpose xi minus xi transpose x plus xi transpose xi. This is the same as x transpose x minus 2xi transpose x plus xi transpose xi, right? Observe here that x is the pattern for which we are trying to find the class membership, and xi is the prototype point of the ith class. That means the first term over here is x transpose x. This is a fixed quantity, and the second and the third term varies for various classes because there is xi there. We need to search for that class I for which this equation is true. This distance is minimum. Let us manipulate this expression a little bit. We just take out this minus sign common to the second term and the third term. We get dx xi square minimum equals x transpose x minus 2 into xi transpose x minus xi transpose xi minimum. Observing this, trying to find the I for which this expression is minimum is equivalent to trying to find the I for which this expression is maximum. 2xi transpose x minus xi transpose xi needs to be maximum because it is after the subtraction sign. With a small change, we can say that xi transpose x minus half xi transpose xi needs to be maximum. I've just taken the 2 common. So, we realize that xi transpose x minus half xi transpose xi needs to be maximum for x to belong to the ith class. Something needs to be maximum. We've heard this before. Which is the quantity for a class that should be maximum so that x belongs to that class? Yes, it is the discriminant function value. This expression indeed represents the discriminant function of that class. We can write the discriminant function as gi of x equals xi transpose x minus half of xi transpose xi. This is actually the expression for the discriminant function of the ith class. This is the value that should be high or the highest or the largest so that x belongs to that class. Look at the equation and we realize that to obtain the discriminant function of a class, all we need is the prototype point of that class, a point that represents that class, the centroid of the class, the centroid of the decision region. Once that is available, it is a function in terms of x. So all we need is the prototype point. Let us now try to draw some equivalence for our understanding. Consider this neural network. Each output neuron represents a cluster. We check for the neuron that gives maximum response to allocate membership to an input pattern X. The output response for this neuron is given as W1 transpose, capital W1 transpose X, capital X, capital W1 transpose capital X plus small wn plus 1. So, this is the output response. For X to belong to the ith class, the output response from the ith neuron should be maximum. Wi transpose X plus Wn plus 1 should be maximum. Wi transpose X plus Wn plus 1 should be maximum. Comparing this expression with the expression for the discriminant function, we notice that it is quite similar. If we substitute Wi equal to Xi, Wn plus 1 is equal to minus half Xi transpose Xi, which means that the coefficients of the discriminant function are the weights of the ith neuron. The coefficients of the discriminant function are the weights of the ith neuron. Oh. Now, let us try to obtain the equation of the decision line between two contiguous decision regions given by the discriminant functions g1 of x and g2 of x. On the line, g1 of x is equal to g2 of x. x1 transpose x, so we are just substituting the formula for g1 of x and g2 of x. So, g1 of x is given by x1 transpose x minus half of x1 transpose x1. And g2x is given by x2 transpose x minus half of x2 transpose x2. We know that x1 transpose x1 is the equation for the norm square. So we substitute that with x1 norm square of x1, and we substitute x2 transpose x2 by norm square of x2, norm of x2 the whole square. And then we bring the right hand side into the left hand side. We take the minus half common and x common, and we finally get this equation, x1 minus x2 transpose x minus half of norm of x1 the whole square minus norm of x2 the whole square equals 0. This is the equation for the decision surface between two decision regions represented by the prototype points x1 and x2. I hope the concepts that were covered in this video are clear. Let us discuss this further in the live Google Meet with the help of an example. See you there. Thank you.